So we had a nebula. Gravity, if we fill in some of the answers here, caused the collapse. Eventually, it pulled it together, formed it into a protostar. It got even more compressed due to gravity, and then nuclear fusion happened. Now, if you remember from last year, nuclear fusion in general is when two smaller nuclei fuse together and form a heavier one. And we had a simple equation last year, and we'll stick with that, even though it's not quite what happens inside a star. But we get isotopes of hydrogen fusing together and forming a heavier element, helium. Okay, in this case, there's also a neutron left over, and it releases loads of energy. So this happens in the core of our star. So stars actually change elements from one type into another. So after the Big Bang, what was mainly produced was hydrogen. Very, very little else. A little bit of helium and some of the lighter elements. Things like carbon and oxygen didn't really exist. They are made in stars during their lives through this process of nuclear fusion. So once our star is born, it becomes a main sequence star, and it is in a steady state. So we have our ball of hydrogen gas, nuclear fusion happening at the core, but the key thing here is gravity still acts. Gravity is constantly trying to pull that star inwards towards the center. And if there was nothing to counteract that, the star would just get smaller and smaller and smaller and hotter and hotter and hotter. However, what we know from year 11 is when we heat things up, they expand. And the same is true of stars. The nuclear fusion that's happening in the core actually produces a bit of radiation that moves outwards and kind of pulls the star with it as well. So we have an outward force here, which you should learn this off, is called gas or radiation pressure. And what that force does is it tries, I'll just draw it inside the star here, to push the star outwards, okay? So gravity pulls it inwards. Due to the nuclear fusion that's happening at the core, we get this force that pushes it outwards. And what happens is those two forces balance. If gravity was to win out and make the star smaller, it would heat up. A hotter core would mean more nuclear fusion, so the expansion force would get bigger, and it would balance out that gravity. If the star was to expand too much, then it would cool down as it expands. The core would get cooler, there'd be less nuclear fusion, the expansion force would decrease, and gravity would put it back together again. So we get this feedback loop that just keeps the star in exactly the same kind of stable size, shape for a prolonged period of time. So our star, the sun, will do this for about 8 to 9 billion years. It's been doing it for about 4.5. So it's about halfway through that sequence. And it's vital for life because it means then it's constantly outputting roughly the same amount of heat, the same amount of energy, and that allows life to evolve. Temperature on the surface of the sun, I don't think you'd be asked this, is about 5,000 degrees centigrade. But at the core, it's much hotter, around about 50 to 100 million degrees centigrade. So we only get nuclear fusion happening at the core. However, that's not the end of the story. So our star, and most stars during the main sequence, are converting hydrogen into helium through nuclear fusion. But eventually what happens is they run out of that fuel. What happens next depends on how heavy the star was to begin with. And we'll just look at a little question at the end of this booklet to kind of wrap this up. So this question asks you to show the life cycle of a star, and we've already done the first bit, so let's fill it in. So we start off with a nebula. Okay, so we have our cloud of mainly hydrogen gas. Gravity acts, pulls it together, and forms a protostar. Gravity continues to act until nuclear fusion happens, and we get our main sequence star, where hydrogen fused into helium. But eventually the hydrogen runs out, and it then starts fusing together the helium into heavier elements. And then once they run out, it then starts fusing other things into carbon and oxygen, and then it starts fusing the carbon and oxygen into heavier and heavier elements. And it can do that all the way up to iron in the periodic table. But as it does that, it kind of expands and cools slightly. So it becomes a red giant. And in fact, during that process, our star, the sun, will actually expand so much it will be out to where Earth orbits at the minute. Now, Earth will move slightly further away, but it's still going to mean Earth gets very, very warm towards those last stages of our star's life. Once everything's fused that it can fuse, it runs out of fuel and it just stops undergoing nuclear fusion. Now, the outer parts of the star just float off away as what's called a planetary nebula, and we're left with the core that initially will be white hot, so it then forms a white dwarf. But eventually, like a cup of tea sitting on the desk, it will cool down and become a small remnant of our star, a black dwarf. And that's what's going to happen to our star, the sun. However, that's not what happens every star. So if a star is bigger, it doesn't form a red giant, it forms what is called a red supergiant. So it will be even bigger than what happens to our star. If it's just slightly heavier than our star, well, in fact, both of these will go supernova, which is at the end of the star's life, when nuclear fusion stops happening, we don't have that expansion force anymore, and gravity then just pulls the star in a massive implosion. When stars do this, they produce a huge amount of energy, and it's actually only then that the energy is high enough that you can produce the heavier elements in the periodic table. So if you look at like a door or a desk, the wood in that was made during a star's life, but anything higher than iron in the periodic table, such as uranium and things like that, they're only produced when stars die in a supernova at the end of their lives. Now, what's left behind after that is a very dense star called a neutron star. However, if the star is really, really massive, the whole mass that was there in the star just collapses in itself to a point, and we call that a black hole. And it's so dense and contains so much matter that within a region close to it, even light can't escape it, and that's where it gets its name from, a black hole. So you should learn this kind of sequence and be able to describe each of those steps.